Welcome student. Hope all of you are doing well. Myself, Professor Dr. Prakash M. Gade, working as an associate professor in School of Mechanical Engineering, MIT World Peace University, Pune. Now in the applied thermodynamics subject, up till now we have covered the steam generator unit, then IC engine components, wall timing diagram, then SI engine units we have completed totally, and recently we have completed CI engines. Hope all of you understood all these units very well. Now today we'll start with the new unit, that is performance testing of IC engines. Now in performance testing of IC engines, we'll be studying the different engine performance parameters, then measurement of brake power, friction power, indicated power, fuel consumption, air consumption, heat balance sheet, performance characteristics, and introduction to supercharging and turbocharging. See, whenever we are testing any engine, so we are finding it performance characteristics, also what are the different performance parameters on which we can characterize the performance of the engine. Also, if you want to compare the different engines, which engine is performing better, so based on these performance characteristics, you can decide which engine is doing better. There are different parameters. You can see the different parameters, performance parameters are there. Along with that, the brake power, friction power, indicated power, fuel consumption, all we are going to study in the testing, that is performance testing of IC engine. But in today's lecture, we'll be concentrating on IC engine performance parameters. So today we'll see the IC engine performance parameters. Now there are different engine performance parameters. These parameters will be studying in detail, or will discuss in detail in this lecture. The first is the indicated thermal efficiency, then brake thermal efficiency, mechanical efficiency, volumetric efficiency, relative efficiency or efficiency ratio, mean effective pressure, and specific fuel consumption. So for any engine, the performance parameters, when you are finding out, you have to find out what is the indicated thermal efficiency, what is the brake thermal efficiency, what is mechanical efficiency, what is volumetric efficiency. Depending on all this, we'll be testing the engine. Now first we'll see the thermodynamic analysis of the engine cycle. Now you can see here, this is the cylinder and this is the piston. So this is the just that is block diagram of piston and cylinder arrangement. Okay, so this is the piston and this is the cylinder. It's just a schematic of the piston cylinder engine, that is IC engine. So in this engine, that is, this part is the part which is above the piston. All of you know that this is what the combustion chamber. So in the combustion chamber, we are burning the fuel. Here we are burning the fuel. So whatever the fuel energy that is generated, or the energy that we are getting after burning the fuel, is that we can consider that this is the energy where we are getting after burning the fuel in the combustion chamber. Now this is the input energy, that is, this is, if you are considering as it 100% energy that is coming into the cylinder, that is inside the cylinder when you are burning the fuel. So out of this energy, now whatever the energy that is generated because of the burning of the fuel, it will increase the heat inside the cylinder and also the pressure inside the cylinder. So with that pressure, whatever the pressure, that pressure will act on the piston to push the piston down, and that stroke we are knowing as the expansion stroke or power stroke. Now out of this 100 units of energy, that is energy in fuel, part of the energy is used to push the piston down. It is not like that all the 100% energy in the fuel is used to push the piston down. There are some losses, and these losses are what? Energy losses. So the energy losses, see, whenever heat is generated, the cylinder of the engine will get heated, and surrounding that there is coolant. Okay, in the surrounding the engine there is coolant, or it is water cooled or air cooled. So the heat is lost to the surrounding. So part of the energy that is generated inside the cylinder, part of it is lost to the surrounding, and part of it is used to push the piston down. So whatever the power that is used to push the piston down is known as the indicated power or indicated energy. So this IP is what the indicated power. So indicated power is what? The energy in fuel minus the energy losses. So 1 minus 2 is your indicated power. So whatever the power that is used to push the piston down is known as the indicated power. So indicated power you will get above the piston. That is from the energy in the fuel, part of the energy in the fuel is used to push the piston down, and that power is known as the indicated power. Now when the piston is moving down, you know that you have studied the components, you know the basic nomenclature and the components of IC engine. Then from the piston, whatever the push it is getting from that energy or from the indicated power, the piston will move down, and that power will get transferred to the crankshaft. So when that power is used to, that is when the piston is reciprocating, moving down, it will convert the reciprocating motion in the rotary motion of the crankshaft. So the power, that the output power or the useful power that we are getting at the crankshaft, and that power is known as the brake power. So this power that we are getting at the crankshaft is known as the brake power. Now the indicated power and the brake power are not same. That is, whatever the power that is used to used to push the piston down, same power is not the same power we are not getting at the crankshaft. So the brake power is less than the indicated power. Why it is so? See, when the piston is moving down, there will be some friction between the piston and the cylinder. Also, there is small end bearing, big end bearing, the friction is in the bearing. Then at the different parts of the IC engine, there are friction. So because of that, whatever the indicated power, the total indicated power we are not getting as the brake power. So there is some loss, and that loss we are calling as the friction loss. So whatever the loss that is because of the friction, then the pumping and unaccounted, all these we are considering as the friction power or friction loss. So from the indicated power, the brake power we are getting, but the brake power is less than indicated power. By which amount? By this friction power. So if you see the thermodynamic analysis, so energy, that is fuel we are burning inside the cylinder, air fuel mixture we are burning in the cylinder, then it will generate some energy. So part of that energy is used to push the piston down, and whatever that part of energy is used to push the piston down is known as the indicated energy or indicated network or indicated power. And whatever and this indicated power is less than the energy in fuel by the amount of this losses. Then when the piston, that is indicated power, then from that indicated power the piston will push down, and the power that we are getting at the crankshaft is the brake power, and brake power is less than the indicated power by this amount, that is the friction power. So there is friction loss. Now if you can see here another block diagram showing just blocks of the energies. So you can see this is the first block, it is the energy in the fuel. So if you are considering this box size is the energy in the fuel, part of this energy is used as the indicated power. So you can see there energy in fuel, it is shown over here, part of that is used as the indicated power. So this remaining part is nothing but the energy losses in exhaust, coolant, radiation and etc. So this you can see the second point over here. So same is represented in the other way. Then from the indicated power we are getting the brake power. So brake power is less than the indicated power, and there is loss, this energy loss is because of the friction and pumping. This all we are considering as the friction power. So we are getting the indicated power less than the energy in the fuel, and brake power less than the indicated power. So this is the energy analysis of the engine. Understood? So you can see this, the indicated power is equal to the brake power plus friction power. So whatever the indicated power that we are getting is equal to the brake power plus this friction power. So indicated power is equal to brake power plus friction power. Now we'll see the different performance parameter. The first performance parameter is the indicated thermal efficiency. Now indicated thermal efficiency is the ratio of energy in the indicated power, that is IP, to the input fuel energy, that is energy in the fuel per second. So if you can see this diagram again, this is the energy in fuel and this is the indicated power. So see, efficiency is what? Output upon input. Now it is indicated thermal efficiency, that is out of this total thermal energy whatever given by the burning of the fuel, how much amount of this energy is used to generate the indicated power or to produce the indicated power. So this ratio of indicated power to the energy in fuel will give the indicated thermal efficiency. So indicated, suppose the indicated thermal efficiency is 30% or 40%, then what is the meaning of that? That means if it is a 30%, then the 70% is lost in this energy losses of exhaust or coolant and radiation losses. So indicated power is less than the energy in the fuel, and that we can get from this formula, that is the indicated thermal efficiency. Why? How much percent the indicated power is less than the energy in the fuel. So that ratio, that is known as the indicated thermal energy. So what is it? Is the ratio of energy in the indicated power to the input fuel energy. So this is the input fuel energy, that is energy in fuel per second. So indicated thermal efficiency equation is indicated power either in kilowatt or kilojoules per second and energy in fuel per second, that is kilojoules per second. So how we are writing it? Indicated power. Now energy in fuel per second we are calculating is m dot f into CV, where m dot f is what? Mass of the fuel per second, that is mass of the fuel consumed per second, and CV is the calorific value of the fuel. So this will give you the amount of energy that is given by burning the fuel and indicated power. So out of this energy, how much percent is used to generate the indicated power? That is given by the indicated thermal efficiency. So this is what the indicated thermal efficiency. Next we'll see the break thermal efficiency. Now in the indicated thermal efficiency we have compared the indicated power with the energy input. Now here we'll compare the break power with the energy input. Now so this break thermal efficiency will give you the percentage of energy, input energy, that is useful, that is converted into the break power or useful power. So the break thermal efficiency, it is also the ratio of the energy in the break power to the input fuel energy, that is energy that is supplied by burning the fuel. So it is the ratio, that is break thermal efficiency is the ratio of the break power to the energy in fuel per second. So break power upon energy in fuel per second. So this is the break thermal efficiency is equal to break power upon this input energy. As I already told you, that is input energy we are calculating as mass of the fuel into its calorific value. So m dot f is the mass of the fuel per second and CV is the calorific value of the fuel. So from this we'll be calculating or we'll be finding the break thermal efficiency. So see, mainly we are interested in break power, so that is the useful power. So break thermal efficiency is very important parameter for any engine. So whenever you are finding out the break power, so how much percentage of input energy is converted into the break power, that is very important. So this is break thermal efficiency. Next parameter is the specific fuel consumption. It is also one of the important parameter because as you know, the fuel prices are very high and the engine should consume minimum fuel consumption. So we have to find out how much that engine is consuming the fuel. So based on that we'll be finding out per unit power. So that power either we are considering as the brake power or indicated power. So specific fuel consumption, it is the ratio, it is the ratio of the fuel consumption per unit time. So this either kg, normally we are taking as the kg per hour. So kg per hour is the amount of fuel consumed per hour. So unit is kg per hour per kilowatt. So per kilowatt, either indicated power or brake power per kilowatt, how much amount of fuel is consumed, that is given by the specific fuel consumption. Now the specific fuel consumption may be the brake specific fuel consumption or indicated specific fuel consumption, depending on depending on the basis of either you are taking this as the brake power or the indicated power. So if you take this as the brake power, then this SFC will become BSFC, that is brake specific fuel consumption. If you are taking this as an indicated power, then this will become as the ISFC, that is indicated specific fuel consumption. So this is brake specific fuel consumption, and this is the indicated specific fuel consumption. Okay, so this is specific fuel consumption. Unit is kg per kilowatt hour. So unit of this specific fuel consumption is kg per kilowatt hour. Now this mechanical efficiency we will see in the next few slides. Now mechanical efficiency. Now as you see that from this input energy is converted into the indicated power, then from indicated power we are getting the brake power. So this indicated power and brake power, so there should be some relation, that is how much percentage of brake power is converted, that is converted from the indicated power, that is how much percentage of indicated power is converted into brake power. So that we want to know. And where is the loss, or how much percentage of loss is there for converting indicated power into brake power, and that loss is nothing but, as I already told, that loss is nothing but the friction loss. And the friction loss is that is in friction loss there is friction between the piston and cylinder, and also the some bearings are there and some parts of the engine. Because of the friction in between these parts, there is loss in the power. Also pumping losses, that is pumping means some pumping losses means suction and the exhaust stroke. So during suction and exhaust stroke, some part of the power of indicated power is used to have that suction and the power stroke. So that we are considering in this friction power. So this is nothing but the friction power. So the brake power is less than the indicated power by the friction power, and the mechanical efficiency is the ratio of the brake power, that is the delivered power or the useful power, to the indicated power, that is power provided to the piston. So brake power divided by the indicated power is nothing but the mechanical efficiency. So mechanical efficiency is brake power upon indicated power. And indicated power, as I already told you, indicated power is the summation of the brake power plus the friction power. So here brake power upon this indicated power is brake power plus friction power, where FP is the friction power. So this is the mechanical efficiency. Mechanical efficiency is ratio of what? Brake power upon indicated power. So if you know the brake power and if you know the indicated power, you can find out the mechanical efficiency. Suppose the mechanical efficiency is 80%. Mechanical efficiency, suppose we are getting for any engine the mechanical efficiency as 80%, then where is the loss, or what will be the comment if the mechanical efficiency is 80%? The comment is that the 20% friction power loss is there. Okay, so 20% friction power loss is there, because out of this indicated power 80% is converted into brake power. So the equation is of mechanical efficiency is what? Brake power upon indicated power. Now if you go again to the specific fuel consumption, here you can see the mechanical efficiency is brake power upon indicated power. Now from this two equation, this BSFC, if you know the value of BSFC of any engine and ISFC of any engine, from that also you can find out the mechanical efficiency. So this mechanical efficiency is what? ISFC upon BSFC. If you put this in this equation, you will get BP upon IP. So ISFC upon BSFC, this will also give you the mechanical efficiency. If you know the value of ISFC and BSFC, you can find out the mechanical efficiency. So now we have seen the parameters that are indicated thermal efficiency, then the brake thermal efficiency, then the specific fuel consumption, in that the brake specific fuel consumption and indicated specific fuel consumption, and mechanical efficiency as I told you right now. And this mechanical efficiency, that is, it is ratio of brake power upon indicated power. Now we'll solve some numerical, so you will get an idea of this, how to calculate the performance parameters that we have studied up till now. Now the first numerical, it is a gasoline engine working on auto cycle consumes 8 liters of gasoline per hour and develops 25 kilowatt as indicated power. The specific gravity of gasoline is 0.75 and its calorific value is 44,000 kilojoules per kg. Determine the indicated thermal efficiency. So in this numerical we have to find out the indicated thermal efficiency. What is given data? So fuel consumption is given 8 liters per hour. Then indicated power is given as 25 kilowatt. Specific gravity of the fuel is given 0.75. So from that we can find out the density of the fuel as 750 kg per meter cube. Then the calorific value is given as 44,000 kilojoules per kg. Now we'll solve it. So fuel consumption is given in 8 liters per hour. As you know that the indicated thermal efficiency equation is indicated thermal efficiency equation is indicated power divided by m dot f into CV. So m dot f unit is in kg per second. So we have to convert this 8 liters per hour into kg per second. So first we'll convert it into meter cube per hour, multiplying with the 10 raised to minus 3. Then we'll convert into meter cube per second, dividing it by 3600, and then we'll convert into kg per second by multiplying it with the density. So substituting in the equation for indicated thermal efficiency, so indicated thermal efficiency is equal to indicated power divided by m dot f into CV. So indicated power 25 into 3, that is 25, indicated power 25 kilowatt divided by m dot f 8 into 10 raised to minus 3 into 750 divided by 3600 into 44,000 multiplying by 100. So we'll get the indicated thermal efficiency as 34.1%. After solving this, we'll get 34.1%. So this is how we can calculate the indicated thermal efficiency. Now we'll see the second numerical. Find the brake specific fuel consumption in kg per kilowatt hour of a diesel engine whose fuel consumption is 5 grams per second when the power output is 80 kilowatt. If the mechanical efficiency is 75%, calculate the indicated specific fuel consumption. So we have to calculate the ISFC in this equation. So in also we have to calculate initially the brake specific fuel consumption. So brake specific fuel consumption we have to calculate in kg per kilowatt hour, but the fuel consumption is given in 5 grams per second when the power output is 80 kilowatt. That is, we have to convert this 5 gram per second into kg per hour. So if you solve it, so brake specific fuel consumption is m dot f into brake power is equal to 5 upon 80. So this you will get in 0.0625 grams per kilowatt second, because the fuel consumption is given in 5 grams per second. So that will convert in kg per hour. So dividing this with 1000, you will get kg, and multiplying it with 3600 will get convert into hours. So the final equation of brake specific fuel consumption, that is answer, will get as 0.225 kg per kilowatt hour. So this is brake specific fuel consumption. Now we have to find out the indicated specific fuel consumption, but the given data is the mechanical efficiency. As we know, as I told you, that mechanical efficiency can also be found out if you know the values of brake specific fuel consumption and the indicated specific fuel consumption. So the equation is what? That is, the mechanical efficiency is the ratio of indicated specific fuel consumption divided by the brake specific fuel consumption. So from that equation we can find out indicated specific fuel consumption is equal to brake specific fuel consumption into mechanical efficiency. So substituting these values, we can get the answer of indicated specific fuel consumption is equal to 0.169 kg per kilowatt hour. See, in this lecture, whatever the numericals that we are solving, we are referring the book as a book of Ganeshan, that is V. Ganeshan, Internal Combustion Engines, Tatom Agra Hill Publications, 4th edition 2017. So now we have seen two numericals. Again we'll see some of the examples. Now this next one, the mechanical efficiency of a single cylinder 4-stroke engine is 80%. So the mechanical efficiency is given 80%. The friction power is estimated to be 25 kilowatt. So the friction power is given 25 kilowatt. We know friction power is the difference between indicated power and the brake power. calculate the indicated power and brake power developed by the engine. So given is what? The mechanical efficiency. So the mechanical efficiency is ratio of what? Brake power upon indicated power. So brake power upon indicated power is equal to 0.8. The second given data is the friction power. So we know that friction power is the difference between indicated power and brake power. So indicated power minus brake power is equal to the friction power. So it is 25 kilowatt given. So by using this equation and these two equation, we can find out the indicated power and the brake power. So brake power we can write in terms of indicated power, that is brake power is equal to 0.8 indicated power, and substituting in this equation we'll get indicated power minus substituting brake power is equal to 0.8 into indicated power. Solving this numerical, we'll get indicated power as 125 kilowatt and brake power as 100 kilowatt. So this is a simple numerical. Once you know the equation, you can easily find out the brake power. Now this is the next numerical. A 42.5 kilowatt engine has a mechanical efficiency of 85%. So this 42.5 kilowatt is the brake power that is developed by the engine, has a mechanical efficiency of 85%. Find the indicated power and friction power. So we have to find out the indicated and friction power. If the friction power is assumed to be constant with load, what will be the mechanical efficiency at 60% of the load? So indicated power, that is from this is mechanical efficiency is given 85%, also the brake power is given 42.5 kilowatt. So from that easily we can find out the indicated power. So from substituting in the equation, we'll get indicated power as 50 kilowatt. Then the friction power is what? Indicated power minus brake power. So from this we can easily find out the friction power. So friction power is coming as 7.5 kilowatt. Now next it is given that if the friction power is assumed to be constant with load, what will be the mechanical efficiency at 60% of the load? So at 60% of the load, the brake power at 60% of the load will be 42.5 into 0.6. So the brake power will be 25.5 kilowatt and the friction power is as it is. So the mechanical efficiency is brake power upon the indicated power. Then the brake power is 25.5 kilowatt and indicated power is what? The brake power plus the friction power. Substituting the values, we'll get the mechanical efficiency as 77.3%. So this is mechanical efficiency numerical. Now as we have seen the parameters, that is indicated thermal efficiency, brake thermal efficiency, specific fuel consumption, mechanical efficiency. Now the next parameter is the volumetric efficiency. So volumetric efficiency will give the suction capacity of the engine, that is how much amount of air it has taken into the cylinder. So whenever we are calculating the volumetric efficiency, even though the air fuel mixture is taken into the cylinder, we have to consider only the amount of air that is entered into the cylinder during the suction stroke. So that actual amount of air we are comparing with the swept volume, that is total swept volume. Swept volume of the engine, how we will calculate? That is the bore, that is the area of the cylinder into the stroke length. So area of the cylinder is pi by 4 d square into the stroke length will give you the swept volume. So that much amount of maximum air we can take into the cylinder, that is that with that volume we are comparing with the actual volume of air taken into the cylinder. So the volumetric efficiency is defined as the ratio of the actual volume as reduced to NTP of NTP means normal temperature and pressure of the charge or air drawn in during the suction stroke to the swept volume of the piston. So volumetric efficiency is actual volume of air taken into the cylinder divided by the swept volume. As I told, as swept volume we can calculate pi by 4 d square into the stroke length L. So actual volume of air taken into the cylinder divided by the swept volume will give the volumetric efficiency. Another way we can define volumetric efficiency is equal to volume flow rate of air into the intake system. So volume flow rate of air into the intake system, that is in meter cube per second. divided by the rate at which the volume is displaced by the system, that is also in meter cube per second. So for meter cube per second, m dot a, that is mass flow rate of air in kg per second, and rho is the density in kg per meter cube. Dividing, they will get meter cube per second, and this displacement volume, that is displacement volume into the number of strokes will give you the unit as meter cube per second. So in this way we can find out the volumetric efficiency. Now the next performance parameter is the relative efficiency. So relative efficiency or efficiency ratio is the ratio of thermal efficiency of an actual cycle to that of an ideal cycle. So the efficiency ratio is very useful criteria which indicates the degree of development of the engine. That is, if you are calculating the actual thermal efficiency of the engine and comparing with the ideal thermal efficiency. Now the ideal thermal efficiency is based on the ideal auto cycle or diesel cycle, that is known as the air standard efficiency. So that comparison will give you the relative efficiency. Now our aim, that is when you are finding out the actual thermal efficiency, our aim is to reach near to the air standard efficiency by reducing all the losses. It is not possible to go up to the air standard efficiency, but by reducing the losses we can reach near to the air standard efficiency. So air standard efficiency is limit for the actual engine. So this is what the relative efficiency.